Hello, guys. Am I audible? Today, I'm going to be taking a session on introduction to cryptography. I hope you're all familiar with cryptography. Uh, it must have gotten a short introduction in the first InCTF session. Cryptography is basically involves a lot of crypto systems and stuff, and we encrypt data to keep it safe so that other people cannot see uh, the things that we don't want them to see. It ensures privacy. So encryption is something that helps us achieve this. So what exactly is encryption? So we can say that encryption is the process of converting data into a form which only we can read, and other parties that we don't want to give access to cannot read. So you may have also heard of the term encoding. Uh, Although people think that encoding and encryption are interchangeable, there is a distinct difference. Encoding is meant to transform data so that it can be properly and safely consumed by a different system. Uh, there are some systems or like applications that take data in like other forms that are like maybe they convert them to integers first, or they would convert them into base 64 first to and then perform any operations on the data before returning the output. Whereas encryption is meant to hide data from unintended third parties that have malicious intentions maybe. Encoding, they are usually publicly available schemes that if we know what it is, we can easily get back the original data. For example, we know how V64 works, so we can get back the original data just by knowing that V64 was used. But for encryption, however, let's say it has been like a ciphertext has been XORed by a different ciphertext, a key. But if we don't have the key, we can't get back the original data. So this is a form of encryption. Okay, so ciphers are an important part of cryptography. These are some famous ciphers. You may have heard of some of them. Caesar cipher, Wegener cipher, Hill cipher, monoalphabetic cipher, and ROT13. I'll briefly tell you what each of them do. So Caesar cipher. Many of you may be familiar with Caesar cipher and how it works. Caesar cipher essentially works by taking a ciphertext, I mean a plain text, and shifting each of the values by a certain amount. We are able to choose what the shift value is, and this is kind of what the key is for the startup cipher. So as you can see, if we have the plain text hello world and we shift it by 13, this H transforms into U and E transforms into R and so on. And then we get the ciphertext. And if a third party does not know the shift value, they can't get the original back. This was the case back in the day when they did not have computers to compute this quickly. However, in today's uh, world with all these computers available, this is child's play. We can get back the original text in mere seconds. Vignay cipher. This is a more complicated version of Caesar cipher, uh, where Caesar cipher shifts all letters or alphabets in a text by a certain amount. And this shifts it by the amount that we give as the key. So I'll show you an example of what I mean. Let's say there is a plain text attack and we want to encrypt this and we have the key 11L. Notice that these both are the same length. So how and we get the ciphertext. How do we get this? Okay, so let's take A, and the key for A, the corresponding letter is L. So we shift A by L amounts, which means 11, because L is the 11th alphabet, and so A turns into L because it's the first alphabet. 1 goes to 11, and then T. T goes to is shifted by E because E is the corresponding key of T. So it goes to X. Okay. Now, interesting, right? T here becomes F, not X. This is because the key changes, and so the plain text, the ciphertext also changes along with it. Unlike Caesar cipher, where the shift value will be same. If t is shifted by a certain amount, the next t will also be shifted by same amount. So beginner cipher is way harder to brute force, since if you don't know the key, you can't just brute force every value because every value is changed by a different amount. So we could get like an infinite combination of words. Hill cipher. This is a more complicated cipher, and this uses mathematics. It converts our plain text into matrices and multiplies them. After multiplication, modular arithmetic is used, and here modulus 26, it also reduces the values. This we can convert it back using inverse of the matrix and also multiply it with the same, uh, yeah, the original, the resulting ciphertext can be multiplied with the inverse matrix to obtain the original matrix back. Okay, monoalphabetic substitution. It's a simple cipher where each letter in a message is swapped with a different letter, and the mapping remains the same throughout the ciphertext. Basically, this is kind of the opposite of the cipher we talked about previously, Wigner cipher. Here, for example, if A maps to L, all A in the plain text will map to L. So if you know the mapping of one A, all the A's in the plain text can be converted, ciphertext can be converted back. So yeah, this is what it look like. Okay, rod 13. Rod 13 is basically Caesar cipher, but the shift value is permanently 13. So you may have heard of other types of rod ciphers like rod 5 or rod 47. Specialty of rod 13 is that since it is exactly half of the number of letters in the alphabet, you can just encrypt the ciphertext again to get back the plain text. So you can shift something by 13 and shift it again by 13 to reach the original plain text. And the Enigma machine, you may have learned this in your school, or you may have come across this sometime while browsing the web. The Enigma machine was used by the Nazis to send secret messages to each other and communicate. But then this was cracked, and this played a huge role in being able to stopping encryption, and like they broke this crypto system, and like uh, they had basically won lots of battles because of this, right? Lots of things had become trivial because this had been broken. So this is the importance of crypto systems. If they are broken, the like a large part of the world will be affected, and even economy and politics, everything can be affected. And how an Enigma machine works is they'll have settings, and if the settings are set to the same, if the settings are same, then you can get the ciphertext and plain text back. Okay, so Caesar cipher. Let's see an example of how we can break Caesar cipher. Okay, so this is a ciphertext, and we need to find the plain text. Since this is a Caesar cipher, we know that this can only have a possible 26 different combinations, 26 different shift values. So if we brute force them all, then we can get back the original plain text. What is brute forcing? Okay, brute forcing is a very prominent thing in the field of cryptography because uh, anything can be brute force technically, but if there is an attack that is better than brute forcing, like the time complexity for a certain for brute forcing a certain crypto system or encryption, if there is an attack that is better than that, even by a little bit, we can say that that crypto system has been cracked, even though in practice we may not actually be able to crack them. So brute forcing is used as like a basis, and it's like one of the fundamentals of crypto. So brute forcing is what we are going to be doing to break Caesar cipher, and it is sufficient to break the cipher since it's not very complicated, and unlike beginner cipher. I'm going to be showing you a website that you can use to do these kinds of things easily. It's called CyberChef, and here you can see you can choose from many of the encodings given here to convert your ciphertext or plain text. You can also do other things. You can search here what you want. So we'll be doing raw 13. Wait. Yeah, okay. Raw 13 brute force. This is basically what I was talking about, and this website is able to do this for us. So these are the plain text that we get from brute force, and if we shift it by one value, two value, three value. So let's try this, shall we? So here, when we reach 17, we see that we get an actual plain text that is intelligible. Uh, and all the others don't make any sense. They're just random letters. So this is how you break Caesar cipher. We can also do this in Python. I'll show you how it's done in Python. So as you can see, this is the ciphertext that I gave. So when we run this, we are going to get back. Lisa didn't think this through. This is because the first letter I gave is capital, and the function that I've written here only decrypts for small letters. So how do we do this for capital letters? Okay, so now we get back the original plain text. So this is how you can use Python to uh, brute force Caesar cipher. If you wanted to brute force this, you could put another loop outside this and change the shift values each time and brute force and print the values for each loop. So I'll explain how this code works. So here I'm initializing an empty plain, empty string, and then in this loop, I'm going to be iterating for throughout the length of CT. CT is this ciphertext. And then I'm going to check if the ASCII value of the first letter of CT, zero, zeroth element of the string, is greater than or equal to 97. Because 97 is the first letter of A, I mean alphabets A in ASCII, and 122 is the last Z. So if it is greater than or equal to 97 and less than 122, this will this will convert by increasing the letter by the shift value we have given. So here is a result string that is empty. To this we append. So first what we do is we take the first letter, we convert it into the ASCII value. Odd will convert the value here, the letter to its number equivalent, and then we'll subtract it by 97. So this number is either if even if it's A and it's 97, the value, it'll go to 0, and then we'll increase it by the shift amount. So let's say I think it'll become like M, and then we give it modulo 26, because in case it's like a letter like R and we increase it by 13, it'll go past Z, and we want it to stay between A and Z. So after applying modulus, we change the number back to the original ASCII value by adding 97 back to it. So we will basically arrive at the original boundary, and the shift value will have been added to it. And we make sure that it stays within the boundaries too. So this is how the string is appended. Here we have given an elif condition for capital letters. Capital A starts at 65 and ends at 90. So this code altogether will convert a ciphertext completely into plain text using uh, the shift value given. And this else condition is to account for like apostrophe spaces, things like that. So yeah. So when you're implementing Caesar cipher by yourself, let's say you want to make the cipher, uh, you have to first get an input string and shift the amount that we want to shift it by. And then we start iterating through the input string and shift each letter by the shift amount, and add the shifter letter to the result string. That is what I just showed you in Python. Okay. Here's another challenge. I want you guys at home to try this out and see if you can obtain this output given on screen. Yeah, I hope you guys tried this already and obtained the output. So yeah, when we simplify 13, we get this. If you want to try it with code, you could. Yeah, so we'll do that. Okay, so I'll get into more about how cryptography works. So uh, in cryptography, we can say that there are two main types of ciphers: symmetric ciphers and asymmetric ciphers, along with protocols. So protocols are some things you might have heard of. They're like SSH, SSL, things like that. They are used to establish connections and communicate through servers and stuff. Asymmetric ciphers, you may have heard of RSA, Resist Shamir and Alman ciphers. This is a asymmetric cipher because it uses uh, a different key for encryption and different key for decryption. So, okay, you could technically say that Route 13 is symmetric, right? Because we use the same key for encryption and decryption. It's kind of like that. But for symmetric ciphers, we use the same key for encryption and decryption. So let's Route 13 would be symmetric cipher, uh, whereas like Route 5 would not be. So symmetric ciphers can be divided into block ciphers and stream ciphers. Uh, this is what block cipher would look like. So let's say we have a plain text. It's like certain amount of letters long. Let's say 40 or something. So we would divide them into blocks and then run them through the encryption function. So usually it's 16, but depending on the uh, crypto system you're using, it can change. So as you can see, let's say it'll be divided into 16, and you may ask what would happen if the last block is not length 16. Then we usually use a thing called padding, and we add padding bytes to the end of this last block so that it becomes the same length. It's usually like, let's say if we have 10 letters and we need 5 more to pad it, let's 6 more to pad it to 16. So we'll pad it with the byte six times. Or if it's 14 and we need to pad it by 2, we pad it by the byte 2 times. So that's how padding works. So yeah, here the plain text will run through the encryption function, and then we'll get back a resulting plain text, I mean ciphertext, and it'll be fully encrypted. If we use the same key, we will get back the original plain text. So this is how encryption works, and this is how decryption works. And it can technically use for any length of plain text. Stream ciphers, you could say XOR is an example of stream cipher because they are not split into blocks, and each bit is used as a plain text and you know key to be used for encryption or decryption. So how XOR works is the XOR gate. It's like if you have if you have 0 0, the output will be 0. If you have 1 1, the output will be 1. If you have 1 0 or 0 1, the output will be 1. Basically, unlike bits will go to 1 and like bits will go back to 0. This is called exclusive OR. So this is what is happening here. 0 1 becomes 1. 1 0 will also become 1. And then 0 1 again becomes 1. But then 0 0 will remain 0. And then 1 1 will turn to 0. So this is because bits are different. We'll go look at the XOR challenge and I will tell you how XOR functions will work. Okay, so this is another challenge. This ciphertext has been shifted by 5 and then XORed with the key. So how this challenge works is you need to add let's say the length of the ciphertext is like 10 and this is the key. So we need to add the key to itself like 3 times till its length is 9 and then add one more which is k. So it'll be like key and k. Okay, so it'll be 10. So this is what you want to do when you're using repeated key XOR. The key is repeated until it's the same length as the plain text or hypertext, and then it is XORed. So try to see if you can do this challenge. Uh, so this is how you could write an XOR function. Uh, so given CTN key, you iterate through the length of the key. I mean, sorry, ciphertext, and we use different values of the key. So the first letter of key, second letter of key, third letter of key, and then
on 0, right? So when it reaches 3, it gets the remainder comes. So yeah, it returns back to 0. Sorry, Mr. Yeah, so XOR. Yeah, so once the first three letters of the key have been used, it reads back to the next letter K again, and then it keeps repeating until the CT has run out, because in the loop we are given length of CT as the interval. Then we join the letters in this and get back to get back the great answer. And this is basically the CSS cipher thing we used earlier.
Okay, yeah, so this is the code for Caesar cipher plus XOR. Uh, since we have some more time left, let's look at AES. It's a type of symmetric cipher. So yeah, we just talked about this. So yes, you can see the plain text is split into certain number of bytes, and they pass through this encryption function. For now, we are not going to be learning this. It's a bit complicated, but basically all you have to know is a lot of operations happen inside this, and they'll mix, shuffle, and return back a value. And after we get all the ciphertext or plain text back, they are appended together and we can get it back. This is called an electronic codebook mode of encryption of AES. AES is the advanced encryption standard that is commonly used nowadays. It was invented in like 1990, and it is still in use today because it's very fast, and it's the best symmetric cipher we still have. It succeeded DES, which is an older one, which had vulnerabilities and could be cracked. So we switched over to AES. So the most basic mode of encryption of AES is ECB. So how there are still ways to break AES ECB. So we came up with better modes of operation. I'll show you another mode of operation. So yeah, now this looks similar enough, right? But this time we make it more complicated by adding an IV. So here what happens is once encryption is done, we XOR this with the previous block cipher. So as you can see for this block cipher, after the encryption or decryption function has run, we will encrypt it with the previous block. Okay, but since the first block does not have a previous block, we will use the IV as the previous block. So the ciphertext goes to the, this is a decryption. For encryption, ciphertext will go first, and then uh, after it goes through the encryption, it is XORed with the IV, which will be over here, and we get back this value. And then same thing will happen here, and this is XORed with the previous ciphertext. So yeah, it look like this. Plain text will be XORed first with IV, and then it'll go through the encryption function. And this encryption function uses our key. We can choose the key. Just has to be a certain length. And then the ciphertext obtained is XORed with the plain text of the second block, and then passes through the encryption. So this is much harder to break. There are other modes of AES like CTR and GCM. AES normally is a block cipher, but some of these modes of operations can convert it into a stream cipher. So yeah, we look at some asymmetric ciphers now. Okay, so as you know, in RSA, we use a different key for encryption decryption. So I'll give you a brief overview. We'll go through this more in more detail tomorrow. But basically, it involves using some large numbers, and it's harder to perform operations on these large numbers even on computers of modern day. And the public key for this will be an e value, and the private key will be a d value. If you use the same e value to try to decrypt it, you will not get back the original text. So you have to use this d value. How you get the obtain the d value, we'll go into more detail tomorrow. But then, yeah, this is all you need to know for now. We'll first convert in message m, that's in bytes to an integer, and then we'll perform these encryption operations. I'll introduce you to one more asymmetric cipher. Uh, this is a key exchange protocol. Let's say we have two people and they want to communicate, but they don't know that the person is a legit user. So they need to confirm first whether they both are legit people and not like bots or some malicious third party. So there'll be both two public values, P and G. G will be the generator of the field. This field and all involves more mathematics, but basically all you need to know is these two public values will be available to both parties, and P will be used as a modulus value so that it stays within a certain limit and it does not go past. Because modular exponentiation and arithmetic is much more efficient than just going and finding large numbers, which will be very hard to compute for the user who made the cipher is using it and like a third party. So we'll choose an integer between 1 and the modulus p, and we will raise the generator g to that. So let's say Alice chooses a, then we will raise g to a, and we'll get, let's say, capital A. And then Bob does the same thing on his side, where he chooses g and raises it to his integer that he randomly selects between 1 and p, uh, and then he gets the letter capital B, this number, and it's under modulus p, so it'll be within this value. After they obtain this public key, they'll exchange it. So he sends capital B to Alice, and Alice sends capital A to Bob. So once they have each other's public key, they can basically. So now Bob has capital A, right? So he can take capital A and raise it to his own private value. So capital A raised to small b, and Alice can do capital B raised to small a. So basically, what they have done is capital A is what? G raised to A, right? So when you raise G raised to A to B, we are basically doing G raised to A into B. So on the other side, we are also doing G raised to B into A. So it's the same thing. The order does not matter, right? So we get to reach the same number. So now we have confirmed that both parties have the same number, and now we can begin exchanging data. So this is how the key exchange protocol works. If you're interested in how RSA and more modular arithmetic works, you can tune into tomorrow's lecture. But you have seen an example of how it works here, since we have used the modulus value. It basically gives like the reminder of something. So yeah, like a number like 30 divided by 26 gives you a remainder 4. So that is the result of the modulus function. So that's it for today's class. I hope you guys learned some cool and fun crypto methods, I guess. And you've learned more encodings and encryptions now. So yeah, and make sure to never create our own crypto system because it won't be secure. Other people have done it for us, so we can use them and be secure, I guess. So yeah, that's it.